Hello, everyone. My name is Richard Morales, and I'm going to be going over the iron-carbide magnetic nanoparticles and their potential for magnetic hyperthermia poster. Of course, I'm not the only source author for this. I have, of course, Haley Captain, Luz A. Martinez Marquez, Marcos Garcia, and my PI, Ahmed A. El Gendi. And we're from the Department of Physics at the University of Texas at El Paso. And real quickly, as you can see in the abstract, let me go over one major thing real quick. As you can read the abstract, you'll notice I'm using FexCy as a way to differentiate that we're not specifically synthesizing one specific nanoparticle. We are focusing on a wide range of iron carbides magnetic nanoparticles. And so that's why we have FexCy. Now, these magnetic nanoparticles are used in specifically many applications, we'll go over at the very end. But right now, we're focusing on its hyperthermia, magnetic hyperthermia applications. And so we synthesize these particles as a little introduction. And right there, you can see the whole purpose is to inject these nanoparticles within a tumor. And so as they surround the cancer cell, we apply an alternating external magnetic field. These particles will then heat up, rotate through Brownian and annealing motion. So then they can heat up the cancer cells and destroy them at a comforting 40 to 43 degrees Celsius without harming any of the normal cells, as the normal cells have a higher threshold for has a higher integrity, whereas cancer cells will be destroyed rather easily comparatively. So we have a little picture right there. Methodology: we synthesize these magnetic nanoparticles specifically through chemical reduction, as we can prepare our carbon sources like allylamine and CTAC. Now, CTAC is what we call acetyl-trimethylammonium chloride. I do apologize if I butchered that, but that's the closest I get to it. And then, of course, we collect that. We specifically have 4 different samples in this paper where we optimize the CTAC ratio, as we see that the CTAC was a catalyst for optimizing magnetic saturation, lowering hysteresis coercivity, as well as creating the size that we needed for this application. Now, as we prepare the carbon sources, we then chemically reduce the iron pentacarbonyl through chemical reduction purged with nitrogen. And so after we add the iron pentacarbonyl, we then heat and stir for around 45 minutes, where we then let it cool down, and we collect the magnetic nanoparticles thereafter and clean them. Now, with this results in having a very interesting conclusion, where right here in the results section of the conclusion, we can see in the middle we have 300 degrees Kelvin, the VSM, and 50 degrees Kelvin in the VSM graphs, where we can describe the magnetic nanoparticles displaying their superparamagnetic yet soft ferromagnetic properties, having a nearly closed hysteresis loop, indicating that they have low coercivity, which means they can lose their magnetic properties rather quickly once the magnetic field is turned off. And that's exactly what we want here in this application. As we move down to the XRDs, we can see that the XRI diffraction graphs show us how the crystal structure is formed, as well as their phase. Now, we're not producing specifically one iron carbide here. We're synthesizing a variety of Fe3C, Fe5C2, Fe7C3 iron carbides, where we then kind of maximize, or optimize is the right word, the magnetic saturation and lower the hysteresis coercivity. As we can see with the CTAC ratio there in the table in the middle, the higher the CTAC ratio, in this case, the higher the magnetic saturation and lower hysteresis coercivity, which shows our story of how we synthesize these particles. And then you can see from A, B, C, D figures on the bottom of the results that where we have the size and also the structure, where we can identify that through this chemical reduction method, we were able to create and synthesize homogeneous nanoparticles. And so that way, it's a lot easier for the Brownian and annealing motion to take place in order to heat up through magnetic hyperthermia. Now, in conclusion, this kind of gives us an idea that this method is suitable and highly possible for cancer treatment in the very near future, and it's a very exciting way to go about cancer treatment instead of the normal chemotherapy and even drug delivery. But yet, with future applications, magnetic nanoparticles can help in drug delivery, as well as other applications unrelated to cancer treatment, like enhanced MRI contrast, environmental remediation, and industrial energy storage. So there's a lot of practical use for these magnetic nanoparticles in a wide range of things. However, right here in magnetic hyperthermia, there is a very high potential for it to be useful. And so, of course, you can see my references at the bottom, and I do appreciate your time and look forward to presenting this at the conference. Thank you.